Hey guys, so we're on to our last two lessons of calculus, and we're going to do integration by substitution. So go ahead and try the warm-up. Okay, so this is a related rates problem that we saw a while ago. So it says a 50-foot ladder is placed against a large building. The base of the ladder is resting on an oil spill and it slips at a rate of 3 feet per minute. Find the rate of change of the height of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. So the first thing we want to do is draw a picture. So here's my building, here's the ground, here's my ladder. It says it's a 50-foot ladder. That's not going to change. So I'm going to go ahead and label the ladder as 50. Okay, then it says that two things are changing. So the base of the ladder is sliding away from the building. I'm going to call that Y. You can call it whatever you want. So if you called it something else, you don't need to change that. And also the height where the ladder is touching the building is changing because it's sliding down. I'm going to call that X. Okay, so I have two variables. Let's go through what they gave us in the problem. So it says it's slipping at a rate of 3 feet per minute. So that's the rate at which the base of the ladder is changing, the red arrow, the Y. So that means that my dy dt, my change in Y with respect to time, is 3. Then it says find the rate of change of the height of the top of ladder above the ground. So that's my X. So I'm trying to find dx dt. And then finally it says at the instant when the base of the ladder is 30 feet from the base of the building. So they want us to evaluate this when y equals 30. And remember, we're not going to be plugging that in until after we take our derivative. All right, so let's set up our equation. I think I want to use Pythagorean theorem here. So this is going to be x squared plus y squared equals 50 squared. And now I'm going to go ahead and do my derivative. So I get 2x dx dt plus 2y dy dt. And then the derivative of a constant is always 0. So I don't even care what 50 squared is. All right, so at this point, I want to go ahead and plug in everything that I know. So I know that dx dt is what I'm looking for. So I'm not going to plug in anything for that. I know that y is 30. I know that dy dt is 3. I need to know what x is. So I'm going to plug in my 30 into this original equation right here to solve it for x. So I don't have a lot of room. I'm just going to say x squared plus 30 squared equals 50 squared. And if I solve that out, I get x is equal to 40. Okay, so my x is 40. And now I can solve for dx dt. So once I isolate that dx dt, I get an answer of negative 9/4 feet per minute. All right, so today we're doing the substitution method for integration. So when you do integrals, it's a little bit different than derivatives. Derivatives is basically, you can do the derivative of anything, no matter how complicated it is. We have the chain rule, we have the product rule, we have the quotient rule. So no matter what I give you, you can find the derivative of it. When you're doing an integral, it's not quite as easy. So it's kind of like when you do addition, you learn how to do addition, you can add anything. It's like super easy. And then once you go to subtraction, which is the opposite of addition, you have to sometimes borrow and it just gets a little bit more complicated. So this is similar to that. When we do integrals, which is the opposite of derivatives, it does get a little bit more complicated. So if I look at example 1, it says find the integral. And what I really could do here, if I didn't have any other skills or tools, I could distribute x cubed plus x 5 times. I could do it times itself 5 times, which would be very tedious, but I could do it. then I could distribute that with the 3x squared plus 1, and I could get like some humongous polynomial, and then that I could take the integral of. I do know how to do that. But as it is right now, I do not know how to do this. Okay, because we have two things multiplying, we have something with a power on it, we just don't know how to do this. So I'm going to show you guys the substitution method. So let's read through the bullet points here. It says substitute u equal to g of x and du equal to du dx dx, which is g prime of x, to obtain the integral of f of u du. Okay, so what we're basically looking to do here is be able to substitute all this complicated stuff to make this a really, really simple regular power integral. Okay, and just to review, we know how to do integrals when we have just a regular something with like a power, okay? So remember how we do that? We add 1, and then we divide by that, okay? All right. So let's look at this first example. So what we're going to do here is we're going to try to pick a u that when we do the derivative of it, that is also in the problem, okay? So on this one, it looks like my u is going to be x cubed plus x. And the reason why is because then when I do du dx, the derivative of u with respect to x, I get 3x squared plus 1. And that is right there. Okay, so I have both pieces. That's perfect. This is like classic u substitution. All right. So now what I'm going to do is I'm just going to multiply both sides of this by dx. And so now I have du is 3x squared plus 1 dx. All right, so now I'm going to substitute into my integral, and I want everything to get substituted. I cannot have any x's left. Okay, so let's look here. Integral of, okay, this first part right here, x cubed plus x, that's u. The 3x squared plus 1 dx is my du, and now look at that. Wow, super duper simple integral. Integral of u to the 5th du. So this is going to equal u to the 6th over 6. And the last step is to plug back in for u. So my final answer is going to be x cubed plus x to the 6th over 6. And if I were to take the derivative of that final answer, my 6 would come down. This is chain rule. Okay, so let me just show you that. My 6 would come down in front. It would actually cancel with the 6 on the bottom. It would become a 5, and then I would have to do the derivative of the inside for chain rule, so 3x squared plus 1. And so you can see it works out perfectly to do the derivative, and I would get back my original answer. All right, so this is the process. It's called u substitution. So let's just review really quickly. The goal is to pick a u that when you do the derivative of it, it kind of knocks out everything between the u and the du. Everything in the problem is represented. All right, let's try the next example. All right, so on this one, it says secant squared of 5x plus 1 times 5 dx. So the thing that's a little bit tricky about this one is the 5x plus 1, because we actually know how to do the integral of secant squared x. We just know that that's tangent x, right? So on this one, my u, oops, I'm going to use black. My u is going to be 5x plus 1. And my du dx is going to be 5. And I'm just going to move the dx to the other side. Okay, so look here. Here's my 5x plus 1. That's going to replace that. Here's my 5 dx. That's going to replace that. All right, so let's rewrite this. I'm going to get integral of secant squared u du. And the integral of that is tangent u. I want to sub back in my u. 5x plus 1. And we're done. All right, well, let's try number 3. So if this was just x to the 1/2, I could easily do the integral of that, right? I add 1 to the 1/2. I multiply by the reciprocal of the exponent. But the problem here is that I have a 2x plus 1. Okay, so this becomes sort of a chain rule situation. And remember, we don't know how to do that for integrals. If this was a derivative, absolutely no problem. But for integrals, we don't know how to handle that. So now we're going to do a u to u substitution. So I'm going to let my u be the inside stuff, the 2x plus 1, because that's kind of the problem that I'm having here, is that there's multiple things inside the radical. All right, so now I need to find my du. So my du is 2 dx. Notice I'm kind of swooping it all in one step to put the dx on the right here, okay? All right, so here is my 2x plus 1. That's going to go here. Here we have a little bit of a problem because this is 2 dx and I only have a dx. I don't have a 2 dx. So in this case, what I actually want to do is I want to divide the 2 over to the other side. So this becomes 1/2 du equals dx. And now, notice I have my dx that's going to go in here, and it's perfect. All right, so let me show you how this gets written now. So I have my integral of my radical u. My dx is 1/2 du. I'm going to put the du here, and I'm going to put the 1/2 here, because remember, with integrals, we're allowed to take out the constant. So that just makes everything a little bit simpler for me. All right, this is now a regular integral. So I'm going to just really quick rewrite this as a u to the 1/2. All right, remember how we do this? We add 1 to the exponent. So add 1 to the exponent, it becomes 3/2, and then I'm going to times by 2/3, which is the same as dividing by 3/2. Okay, my 2's are going to cancel. So my final answer is, well, not my final, but 1/3 u to the 3/2. Now my final answer is plugging back in for the u. So 1/3 2x plus 1 to the 3/2. Okay, and if you just can imagine in your head doing the derivative of that answer, the 3/2 would come down in front, the 3's would cancel. I would get 1/2 2x plus 1 to the 1/2 by minusing 1 from the 3/2. Derivative of the inside would be 2, which would cancel with the 1/2, and that would be golden. All right, let's try number 4. Very similar to number 3. It says find integral of cosine 7 theta plus 3 d theta. So remember, on this one, if it was just cosine theta, that's easy. I know how to do the integral of cosine, but it's not. It's cosine 7 theta plus 3. So that's kind of what we want to substitute for. So we're going to let our u be 7 theta plus 3. That means my du is 7 d theta. Okay, so my 7 theta plus 3, that's going to go right here. Oops. But here I have 7 d theta, but here I only have a d theta. So I want to divide the 7 over to the other side. So this gives me 1/7 du is what I put in for d theta. So now see here, my d theta is going to be able to substitute in, which means I just need a 1/7 on my integral. Oops. All right, so now I'm going to integrate the integral of cosine is sine, so 1/7 sine u. Plug back in for the u. Done. All right, so hopefully you're getting the hang of the u to u substitutions. Let's try the next part. It says, sometimes we observe that a power of x appears in the integrand that is 1 less than the power of x appearing in the argument of a function we want to integrate. This observation immediately suggests we try a substitution for the higher power of x. So this is just a general tip. If you see you have Well, let's look at example 5. An x cubed and an x squared. You should immediately be thinking u to u substitution, because when you do the derivative of the x cubed, you're going to get the x squared, right? All right, so let's try example 5. We're going to let our u be our x cubed. Notice I did not do e to the x cubed, okay? That would be too complicated, right? If I did the derivative of that, that's chain rule. I would have a lot of extra junk flying around that I don't need. So I'm just going to let my u be the x cubed. Okay, that means my du is 3x squared dx. Okay, let's just look at that really quick. The thing that I have extra that I don't need is the 3. I'm going to divide that over. I do not need a 3 when I'm subbing in. So 1/3 du is x squared dx. All right, so now let's look at everything we have here. We have our x cubed. That's going to go there. We have our x squared dx, x squared dx. All right, here we go. So this gives me integral of my x squared dx is my 1/3 du e to the u. All right, integral of e to the u is e to the u. And now my final step is plugging in for my u. All right. So your homework, notice that I actually gave you the answers on the bottom. They're actually like a helpful hint, not the answer, like a hint for your u. So what I would do if I were you is I would actually fold your paper over, and I wouldn't even look at those unless you absolutely need to. They're just like a little bit of a helpful push, but try to do them on your own. I think you can do it. All right, so I will see you guys after you've tried this homework. We will do 4.6, which is our last lesson.